Recently, I had built a computer with the Zilog Z80 CPU. This is an 8-bit CPU, originally released in 1974. The CPU has a 16-bit address bus, meaning that it can access 64 kilobytes of memory without memory banking. However, recently I wanted to upgrade to something a bit more powerful, so I chose the Motorola 68K. This is a 32-bit CPU released in 1979. It has a 16-bit data bus, meaning that it can move twice the data per memory access as the Z80. And it also has a 24-bit address bus, meaning it can address up to 16 megabytes of memory without memory banking. Furthermore, the instruction set of the 68K is a lot less obtuse than that of the Z80. Most of the registers are more general purpose, so compilers do a better job at generating assembly for the 68K than for the Z80. And this means that I can program the CPU in C with the GCC compiler, which I plan to get to in a later video. Today I want to free run the CPU, which will allow me to test the CPU without wiring it to any memory. The CPU data bus will be pulled down to 0 volts, which will make the CPU think that it is receiving the instruction OX0000. This is an ALU instruction on the 68K, but it will act as if it is a no operation instruction, causing the CPU to go onto the next memory address. This will cause the CPU to cycle through all the memory addresses, and we'll be able to see this by putting LEDs on the address bus. Apart from pulling down the data bus, we also need a reset circuit to reset the CPU when power is applied, and an oscillator circuit to provide the clock for the CPU. I will start with the reset circuit. At the core of the reset circuit is a capacitor and a resistor. When power is applied, the capacitor slowly charges up through the resistor. When the capacitor voltage is high enough, it triggers a Schmitt trigger inverter to turn off. This creates a short high pulse on startup, whose length is determined by the RC constant. A button also allows the user to reset the circuit manually. Now, to reset the CPU, we need a low pulse on both the halt and reset pins. However, both of these pins are bidirectional with open collector drivers. This means that the CPU can drive the reset and halt pins low by itself, which happens when the CPU executes a reset instruction, which allows the CPU to reset external peripheral devices when the reset instruction is executed. So this means that wiring the reset circuit to the reset and halt pins directly would create a short circuit if the CPU executes the reset instruction. So instead I will use a pair of discrete N-channel MOSFETs to pull down the signal during the reset, and a pull-up resistor to pull up the signal during normal operation. The MOSFET also acts as an inverter and inverts the signal from active high to active low like we needed. Next is the clock circuit, for which I will use a 12 MHz resonator. Using a pair of 20 picofarad capacitors and one of the Schmitt trigger inverters, I can create an oscillator with this resonator. Finally comes the CPU itself. All the data pins are wired through resistors to ground. Resistors are needed since the pins are bidirectional. Then all the ground and power pins need to be connected, and a bunch of control signals need to be tied to either high or low. These control signals are strictly inputs, so they can be wired directly to VCC and ground. Finally, the halt and reset pins can be connected to the reset circuit, and the clock pin can be connected to the oscillator. With that done, we can see the CPU going through the memory addresses by putting LEDs on the address buttons. With power applied, you can see the address bits counting up in binary as the CPU counts through the memory addresses. In the next video, I hope to set up GCC to compile code for the 68K and maybe wire up flash memory to see the CPU executing actual code.